be proceeding with the second part of the atomic models, and I will hope that you pay rapt attention. I have a deep dive into my screen now. I'll share my screen, and then we can proceed to the class. So give me some minutes as I construct the board where we will be taking this class. The model of atoms, part 2. Hold on for a bit. I'm still trying to set up the screen platform. Model of atoms. Get your writing materials ready, because it's more of a theoretical discussion, but very pertinent towards your exam. General physics knowledge. Of course, yeah, there we go. Model of atoms, part 2. So let me set this up right. Okay. So I'd be dealing with, like I said in the last class, where I stopped was the electron cloud model is where I'm moving to now. The electron cloud model. The electron cloud model. So this particular model, this model visualizes, excuse me, let me write that properly. This model visualizes the atom as consisting of a tiny nucleus of radius of the order of 10 to the minus 10 to 10 to the minus 15 meter. So let me take that somewhere down. Hold on. So it's kind of taking everything. So I'm just going to erase it and write it so that you know the number I'm writing there properly. I'm going to write it again. Ten to the minus 10 to 10 to the minus 15 meter. So it says the model visualizes an atom that consists of a tiny nucleus of radius of this range. And the electron is visualized as being in rapid motion. As being in rapid motion within a relatively large region around the nucleus. But spending most of its time in certain high probability regions. So this is the idea. So the electron is visualized as being in rapid motion within a relatively large region around the nucleus, or is believed to spend time in spend most of its time in the what we call the high probability regions. Let me tell you this for free as a student. One of the ways to understand things is that you reread them. I mean, you might read them the first time and not get the point, but when you go back, reread it like 2 or 3 times and try to visualize it, it's going to sink down. If not entirely, far much better than the first time you ever read it. So cultivate that habit. So thus, in this model, the electron is not considered as a ball revolving around the nucleus, but as a particle or wave with a specified energy having only a certain probability of being in a given region. In space, outside the nucleus. Outside the nucleus. So here the electron is not considered as a ball revolving around the nucleus, but as a particle or a wave with a specified energy having only a certain probability of being in a given region in space outside the nucleus. Chemists prefer to consider the electron in terms of a cloud of negative charges. With a cloud being less dense, or being dense in regions high energy probability, of high electron probability, and then they are more diffuse in region of low probability. The probability of finding the electron Inside the spherical boundary is high. Ability of finding the electron inside the spherical boundary is high. Probability then decreases rapidly as the distance of the thin shell from the nucleus increases. This last point I just made describes something like this. There is higher probability to find an electron here than to find an electron here. So we say the probability of finding the electron inside the spherical boundary yeah. Let me explain that here. Oh, let me rephrase this. There's high probability of finding an electron here than here. Let me do this. Let me go back. Let me use a green. So you can easily find an electron here than here. So in this kind of setup, we'll call this thing the thin shell. Let me call it the thin shell. I'm just visualizing something for you. Shell. Call this the nucleus. Now, so it said the probability of finding an electron inside the spherical boundary is high. So yeah, within the spherical boundary, let me call that within boundary. So why I label it green is because the probability to find an electron there is high. High probability to find an electron. But there is another one more distant. You know that the distance from here to here is higher than the distance, let me do it like this. Because we are using the radius. Distance from here, okay, hold on. Distance from here to here is higher than the distance from here to here. So as the distance increases, this one is more distant from the nucleus. So let me give this one its own thin shell. So these things are thin shells. I'll make it more standard. So both this is also a thin shell. So that's how is also a thin shell. So, but as the distance of the thin shell increases from the nucleus, this one is more distant, and so low probability of finding an electron there. Now, please, the focus here is the thin shell. You will, let me label this thin shell. You will hardly find an electron on the red thin shell. So the point is, you hardly find an electron. Okay, let me put it this way. There is a higher, there is an higher probability of finding an electron on the green thin shell than on the red, because the green thin shell is closer to the nucleus. That is the idea. Let me see if I can make this black. Let me try to do that again. Okay. Let me try one last time. I can't make this text. I want to make it black so that I can easily see it. Okay, it's fine. So I couldn't do that. Let's go on. Now I've established that, and I'll move straight on to another subheading: atomic structure and chemical behavior. Atomic structure and chemical behavior. So take a minute to get that down. A minute with me. Concentrate myself. So yeah. Atomic structure and chemical behavior. Forgive me if we have some background noise. Now, it is very important that we establish that today we consider the atom is made up of tiny, the massive nucleus at the center. And outside the nucleus is a cloud of electrons which move in wave-like orbits or shells around the massive nucleus. So I'm going to repeat that. So then we'll consider the atom as made up of tiny or massive nucleus. That is, the nucleus looks small, just as in this case. Just using this as reference. This nucleus looks smaller in shape, but we're saying it's heavier. At the center, and outside the nucleus is a cloud of electrons which move in wave-like orbits or shells around the massive nucleus. That's a very simple idea. Now, it is good to note that the nucleus consists of protons which carry positive charges. Nucleus consists of protons which carry positive charges, and neutrons which are neutral. And when we say which are neutral, we are saying which carry no charge. So we've established that. Take note of that. The nucleus consists of protons which carry positive charges, neutrons which are neutral. Neutrons are neutral in the sense that they carry no charge. The neutron and proton together constitute a nucleon. You see that? So neutron and proton, let me give you a formula, equal to, that combination equal to nucleon. Let me put plus here. Well, you see that shell called nucleus? It is more like what contains. It's like the house. The nucleus consists of so it's just like we're going to say the nucleus contains the nucleons. To break the nucleons down, the nucleons are made up of neutrons and excuse me, and protons. So that is the big idea here. So just take note of that. Nucleus made up of the nucleons. Those nucleons simply neutrons and protons. So nucleus, nucleons, neutron, protons, all of that in mind. Or somewhere, all the mass of an atom is concentrated in the central nucleus. All the mass of an atom is focused on the nucleus. So most of the mass, almost the entire mass. So take note of this statement. They are not just random stuff. So the fundamental particles, or let's say subparticles of an atom, the fundamental subparticles, or let's say subatomic, let me put that one. Fundamental subatomic particles we have, we mentioned them. We have are number one, protons. Number two, neutrons. And number three, electrons. Take note of that. It is good to quickly establish that the electron is the lightest particle of an atom. So the picture we've been painting so far is more like, let me do this. These are shells that run pretty much up to the nucleus. In the nucleus, we have protons, neutrons. On the orbits, you can find electrons anywhere. So on the orbit, on the shell's orbit, electrons exist. Now we've said that the nucleus, which contains, this is the nucleus, which contains protons and neutrons, and when you combine them together, they are called, nucleons. I mean, protons and neutrons, when you combine them, they're called nucleons. The idea is that this guy here is heavy. Let me put it like this: heavy, or contains most of the mass of an atom. The entire thing we're looking at here is like the pictorial view of an atom. So it's heavy and contains most mass. That's the nucleus. So meanwhile, the electron is pretty much light. light particle. So that's for the, and the reason why we have, so I'm going to break it down for you. Their masses, I'm going to give you in terms of number. So let me see, let me continue to make the statement by saying so heavy. So the nucleus is heavy and contains most of the mass. Let me continue like what I was saying by saying the electron is the lightest particle of an atom with a mass of 9.10 to the power of minus. Oh no, sorry. Let me do this comment. So the electron is the lightest particle of an atom with a mass of 9.1 times or let me put it like this, not 9.1. Let's say 9. Let me write it like this: 9 times 10 raised to power minus 31 kilogram. So that is the mass. Let me make sure I'm writing it more clearly. With a mass of 9 times 10 raised to power minus 31 kilogram. And an electronic charge of, now we write it like this. Normally I write it with an E, their charge. Now it's negative, of course, for an electron. So, but in terms of magnitude, now we know that it's negative, but the magnitude, the number is 1.6 times 10 raised to power minus 19. So, but most times we just ignore that negative. But you know that in actual, in reality, when we're using numbers to calculate, when we talk about the charge of an electron, we kind of just ignore the negative because this is the magnitude of the charge. So that's this mass and that's this charge. That's for the electron. Now the proton has a mass of 1.67 times 10 to the power of minus 27 kilogram, which is, now see how bigger or how larger the proton is compared to the electron. 1.67 times 10 to the power minus 27 kilogram, which is over 1,836 times heavier than the mass of an electron. So the idea here is that the proton carries, this is the mass of the proton now, it carries positive charge. And yeah, most times, say the electron is written like this. So E minus, while the proton is written with E plus. It carries a positive charge of yeah, that's 1.6. So in terms of magnitude, the electron's charge and the proton's charge, they are equal. It's just the what I would call the sign. The difference is in one is positive, one is negative, but the magnitude of the charges, both electron and proton have 1.6 times 10 raised to the power minus 19. So take note of that. Very important. Coulomb. There is a positive charge, and I've written that. We've written the mass, we've written the charge for a proton. It's also good to establish that there are the same number of protons in the atoms of different elements. There are the same number of protons in the atom of different elements. So we're saying that, oh, number of protons so let me put it like this. There are same number of protons in the atoms of different elements as the number of electrons. So we're saying same number of protons equal to number of electrons. Take note of that. So that's the point we're making. In a neutral atom, the number of, so let me write it clearly out. That is, in a neutral atom, and let me tell you why an atom is said to be neutral. It's because nucleus has positive charge. And why does it have positive charge? Because it is made up of, contains positive and contains proton, which is positively charged, proton, positive, and neutron, which has no charge. No charge. So when you combine positive and no charge, it ends up, the nucleus ends up being positive. So in a neutral atom, nucleus positive, nucleus is positively charged, put that way, charged. That is, contains this, and the electron. So in the nucleus, we have positive charge. Positive charge wins in the nucleus because it contains proton and neutron. And so that's like positive and no charge. So the nucleus ends up being positive, and then the electron. So the atom is made up of nucleus and electron. So, and then the electron is negatively charged. So when you combine positive and negative, the atom is supposed to be neutral. So in a neutral atom, we have just established that the number of protons must be equal. That's for a normal atom. Must be equal to the number of electrons. That being said, we can now discuss more and say we denote the atom of an element by, write it as AZ. Now get a point here that whenever it is written like that, A stands for mass number. For example, you see something like I'm gonna write 1, for instance, and then atomic number. So the idea here is, if you see something like helium now, helium having 4, 2, it means 4 is the mass number and 2 is the atomic number. So let's go ahead and talk about that for a bit. The atomic number or proton number, so it's either called atomic number or proton number, is the number of protons in the nucleus of an element. The mass number or nucleon number. So it's either called mass number or nucleon number. And that is the one denoted by A, is the total number of protons and neutrons in an atom of an element. So the idea is that Z is equal to number of protons. A is the number of protons plus number of neutrons. So that is the idea. And this number of protons is also equal to number of generally is equal to number of electrons. Yeah, the number of protons, because we have said it that in a normal, we've already said it. See it here. So Z being number of protons must be equal to number of electrons, while A is number of protons plus number of neutrons. Now let's talk about something briefly before we call it a day. Isotopes. Isotopes, these are atoms of the same element which have the same atomic number but different mass number. These are atoms of the same element which have the same atomic number but different mass number. So the idea here is that you can have an element that has A, Z, and that same element has the same Z, that is same atomic number, but another A, a different kind of A. Maybe let's say B. Let's have B here. So Z is the same thing, element is the same thing, but the mass number are not the same. And what causes that? So let me write it first, that isotopes are those atoms with the same number of protons but different number of neutrons. So that's, I just stated what is the cause of that. You see that the atomic number or number of protons the same, the element the same, but the mass number is different. It means that this particular element has same number of protons in both cases, but different number of neutrons. So it's the number of neutrons, different number of neutrons, that makes isotopes to exist. So it means that A and B, in A will be made up of Z plus a particular number of neutrons. I'm going to call it Na. While B is made up of Z plus a particular number of neutrons called Nb. The difference between Na and Nb is what makes A and B to be different. Because normally Z and Z is the same in both. So that is the idea. We must take note that isotopes have similar chemical properties because they have the same number of electrons around the nucleus. So they have the same number of electrons around the nucleus. So that makes them to have similar chemical properties. So most of the chemical properties depend on the number of electrons. So since they have the same number of electrons, they should have similar chemical properties. So another thing to let me mention that examples of isotopes. Let me give one here. You have 3517 chlorine, and that one has 17 protons and obviously 18 neutrons, because once you add that, that's what gives you 35. And there is another chlorine that has 3717 chlorine. These are real life isotopes. This one has 17. Now the same thing, you know that once it has 17 protons, it also has 17 electrons. I mean, that's just like natural. So let me put it. So 17 protons, those are 17 electrons. I mean, so this one too has 17 protons, which is equal to the number of electrons, 17 electrons. But this time around, it has 20 neutrons. You discover that 17 plus 20 is what gives you 37. You see that? That is the idea. So meanwhile, here, 17 plus 18 is what gives you 35. So these two things are supposed to be the same. These two things are the ones that are different, and that's what makes isotope. And what causes that difference is the difference in the number of neutrons, because both number of protons are the same. So that's an example of isotopes, and that exists in what we call this Cl is called chlorine. Must be used to that by now. Then there is another one. Just going to take another one. Say for instance, uranium 238, 92. In this case, we have 92 protons, which is equal to 92 electrons. And then we have 146 neutrons. And then there is another one, 235, and then 92. In this case, we have 92 protons, 92 electrons, but we have 143 neutrons. Another form of uranium still exists, 234 uranium, 92 protons, 92 electrons, but then we have 142 neutrons in this case. So in everything we see different forms, but all their atomic numbers are same, but their mass numbers are different because the neutron numbers are different. So having established this, we'll continue in our next class with a different topic. We'll be going to radioactivity part 1. I'll see you in the next class.